Since the turn of the century, every nation boasting a navy has operated a submarine fleet. And virtually every year, some of these undersea ships are lost through mishap. These accidental sinkings can be caused by collision with a surface ship, sometimes by machinery failure, or pressure hull failure, or simply by means of a hatch that never closed. In the immediate hours following a submarine disaster, the one and only concern is the safe recovery of the crew. As long as hope of survival exists, all efforts are bent to this task. When the last survivor has been accounted for, the rescue phase is complete. At that moment, a new task faces the Navy: salvaging the submarine itself. The salvage of any type of ship is a long, tedious, and challenging job. A great deal of effort is spent behind the scenes, studying builders' plans and computing lifting forces. The tasks that must be accomplished are at best hazardous. The special equipment and methods employed by the salvage forces are the result of a half-century of experience. Each item on the inventory and each engineering technique was developed to overcome some specific problem on a past job. Because no two salvage operations are exactly alike, there can be no standard formula for raising a ship. However, there are basic principles which remain unchanged. By applying these principles to the task at hand, the job can be made easier and the chances for successful salvage greatly improved. The first major step is to prepare a salvage plan. To do this, the planners must evaluate the environment, choose a lifting method, and determine the lifting force. Nothing is more important in any salvage operation than the preparation of a thoroughly thought-out plan. The initial planning phase often takes place where the submarine was built. The salvage officers establish a temporary headquarters in the shipyard and begin gathering the information they will need to form their plan. With the submarine survivors safely recovered, time is a less critical factor. Shipyard representatives, naval architects, and marine engineers form a technical advisory group, supplying the salvage team with the data they will require on the ship itself. These specialists, operating out of the shipyard, remain on the project throughout its duration. As facts are gathered on the submarine, the ocean environment is also studied. Oceanographic experts may be consulted for an accurate description of the sea bottom. Does the submarine lie on hard sand, or can the divers expect deep mud? How about coral, large rocks? Depth itself is critically important. This determines what kind of work divers can be expected to do. Depths approaching 300 feet severely limit the type of task a diver can accomplish, at least with today's technology. What is the prevailing weather? If winter is approaching, diving may be impossible. Air hoses will freeze up. Unstable diving platforms will severely endanger the lives of those tethered below. The planners must know everything about the physical state of the submarine at the time of sinking. Important information can come from interviews with survivors. the men assigned to the underway watch, the engineering log keepers. What valves were open? What compartments flooded? Was internal damage sustained? The shipyard representatives, that is, the people who built the submarine, render invaluable assistance during formulation of the salvage plan. Once internal damage is suspected, they list the work that must be done to make the hull airtight. Certain damage may be so great that it would be futile to try to repair it underwater. But at least, the salvage officer gets a frank and realistic appraisal of his problem at the outset. At some point during the planning phase, a diving survey must be made. A part of this survey may have taken place during the rescue operation. In any event, the planners will require an on-the-spot report of the submarine's condition. How does the submarine lie? Is there a list? If so, ballast tanks, normally open on the bottom, will not hold air. How about external damage, particularly if the sinking was due to collision? Are there any open hatches? Most important, is the hull partially buried? If not, lifting wires can be swept under the bow and stern. By this time, the planners should have enough general information to choose a lifting method. There are 4 principal methods of raising a submarine: patch and pump, pontooning, self-lift, and lift ship, or a combination of any or all of these. Procedures for patch and pump are identical to those used in the raising of any type of craft. The hull must be made watertight. This means, of course, repairing all damage, inside and out. Cofferdams are built, if necessary, to extend the watertight hull to the surface. The ship is dewatered until it achieves enough buoyancy to lift itself and resurface. This method is ideal for shallow depths, and particularly when mishaps occur alongside the pier. One drawback: patch and pump requires more divers' time than any other method. This is due to the underwater repairs needed to dewater the ship. Because training material already exists on this method, it will not be discussed further in this film. Pontooning is the only practical method by which a submarine can be raised in deep water in the open ocean. Because divers are needed to perform certain preparatory tasks on the submarine itself, the maximum depth at which pontoons can be used is limited to the diver's safe working depth, or 300 feet. The submarine can also be raised by lift ship. This is a simplified view of the stern gantries. All rigging not essential to a stern lift has been eliminated. These are the same ships, now rigged for a belly lift. Again, all rigging not essential to the belly lift has been eliminated. With this method, the ships are pinned down to the submarine at low tide. As flood tide begins, the submarine is raised a distance equal to the tide range. This is normally used in shallow water only. Choice of lifting method is influenced by depth, by availability of ships and equipment, and by the time factor. If time were critical, patch and pump should be abandoned in favor of lift ships or pontooning. And if lift ships are not available, the salvers would use pontoons. To determine lifting force, start with the weight, or displacement of the submarine. Then add any suction effects due to bottom conditions. The total of these 2 factors is your lifting force. In the case of the S-51, 800 tons for the submarine itself, plus 200 tons to overcome mud suction. Thus, 1,000 tons of lifting force were needed. Plan to obtain this force by combining external lifting techniques, such as pontoons or lift ships, with self-lift. In self-lift, the lifting moments are obtained by blowing down submarine compartments and ballast tanks. Damage to the submarine hull determines how much self-lift can be achieved. If the submarine lies at an extreme depth, few, if any, repairs can be made. Theoretically, any ship can be raised if enough external force is applied, but is more practical to first obtain as much self-lift as possible, and then make up the difference with external lifting methods. At some point during the planning phase, the salvage organization will shift its headquarters to the site of the sinking. The second major step is to rig for lift. To do this, they must pass the lifting wires and then prepare for self-lift. Once the lifting method has been determined, wires must be placed under the hull. The number of wires and their exact placement depends upon a number of planning factors: the lifting method, the submarine's physical state, and even her hull design. Sweeping a messenger under the hull by small boat is the easiest and fastest method. However, this can be done only when one end of the submarine is sufficiently clear of the bottom. In most cases, one end of the submarine, and sometimes both ends, require either tunneling or lancing to pass the messenger. Depth determines the method to be used. If bottom depth is less than 100 feet, divers can wash out a tunnel under the hull. In tunneling, an ordinary 2.5-inch fire hose with a tunneling nozzle is used. Rearward jets on the nozzle tend to equalize back pressure on the hose, enabling the diver to manage relatively high water pressures. Another effective method is lancing, with the diver working from the deck of the submarine. A curved lance, designed to conform to the submarine hull, is worked under the ship. This is a long and tedious operation, but a relatively safe one from the diver's standpoint. There are two methods of leading the messenger around the hull. One way is secure the messenger to a pad eye so that the lance leads it around the hull. In the second method, the hose is disconnected and a small wire messenger, similar to a plumber's snake, is fed through. Another messenger is sent from the surface and the wire is bent to it. This wire leads progressively larger messengers around until the lance itself is straightened by the strain and is brought to the surface. If more than one lifting wire is required, a founder's plate attached to the messenger leads 2 or 3 other wires around at the same time. Normally, a chain sling is used to cradle the submarine during the lift. The lead end of the chain is fitted with a fairing cone to prevent it from becoming hung up on hull projections. The lifting wire draws the chain sling in place. At the same time the lifting wires are being rigged, the submarine hull should be prepared for as much self-lift as possible. Each submarine is made up of a number of watertight compartments housed within a pressure hull. Because of this hull's great structural strength and inherent watertight characteristics, submarines are more easily adapted to self-lift procedures than any other type of ship. Outside of the pressure hull are a series of ballasts and fuel tanks. If the pressure hull is flooded because of extensive damage, underwater repairs may be impossible until the submarine is brought to shallower water. Therefore, when faced with a flooded pressure hull, the salvage force will normally have to obtain self-lift from the outer tanks. The amount of self-lift possible varies with the type of submarine. The easiest method of obtaining self-lift is by blowing compressed air into flooded ballast and fuel oil tanks. Salvage air fittings have been provided on all U.S. submarines in current use. Air pressure applied through the salvage air fittings at the tank top expels seawater or fuel oil through the bottom vent, which is open to the sea. A captured air bubble remains in the tank as long as air pressure greater than sea pressure is maintained. However, if the submarine heels over during her lift, this trapped air will be dumped. Therefore, stability during the lifting operation is critical. Using a sister ship, familiarize the divers with all tasks they must perform. Locate salvage air fittings as well as other external valves or openings that must be gagged or sealed. If the submarine is at such depth that divers can enter the hull to perform underwater tasks, it is paramount that they rehearse each step aboard the sister ship. The task may appear simple, but in total darkness, encumbered by lifelines and power cables, even the identification and turning of a valve can become a complicated job. In preparation for the lift, a salvage air hose is connected to each compartment and tank to be blown down. Normally, these hoses are lashed together at a central point near the deck and led to the surface as an umbilical. Each hose is connected to an outlet of the salvage ship's air manifold. In this manner, the air pressure in each tank and compartment can be individually controlled during the lift. The third major step is to execute the lift. This can be through raising with pontoons, raising by lift ship in a stern lift, raising by lift ship in a belly lift, or by self-lift. Pontoons have been used successfully on several major submarine salvage operations since their first employment on the F-4 off Honolulu in 1915. The step-by-step procedures required to rig pontoons for a lift are too lengthy to cover in this film. However, some major principles as well as cautions will be offered. If the submarine lies in relatively shallow water, pontoons are secured close to the hull and the ship is surfaced in one lift. However, in most cases, the submarine will lie at such a depth that it must be lifted in several stages. The critical part of the operation is raising the submarine to the depth intended, and no farther. This is done with the uppermost pontoons, called control pontoons. Control pontoons are blown first. Then lower pontoons and submarine tanks are blown on a careful schedule until the submarine achieves positive buoyancy and rises. As the control pontoons surface, the buoyancy they contribute to the total of the lifting moments stops. The remaining lifting moments are insufficient to raise the submarine further, and it is held at the desired depth. The most critical planning step is ensuring that adequate control is provided in the upper array of pontoons so that the submarine will stop rising the moment the control pontoons surface. When the submarine has been brought to the intended depth, the entire array is towed to shallower water. The salvage ship continues to supply air until the submarine can again be grounded. Pontoons will be repositioned and the process repeated. These are the YHLCs, the Navy's heavy lift ships. Originally built in Germany during World War II, they proved effective in raising submarines as well as other types of ships. They were subsequently turned over to the United States, where they saw extensive duty clearing harbors in Southeast Asia. In picking up a ship as large as a submarine, the YHLCs must be used as a pair. The two ships, when rigged to lift the submarine with their stern gantries, can lift a total of 1,200 tons. The length of the purchase limits the lifting distance to 100 feet. These ships, when rigged for a belly lift, exert a much greater lifting force. Each ship can lift 2,400 tons, or a combined total of 4,800 tons. We'll take a closer look at both lifting techniques, starting with the stern lift. When lifting over the stern, the spacing of the lifting wires is critical. Because the YHLCs were designed in Germany, All design measurements are in meters. The gantries are spaced 10 meters, center to center. If the lifting wires were rigged off-center, an undue athwartship strain would be placed on the gantries, with extensive damage resulting. The first step in rigging for the stern lift is to accurately mark the bow and stern of the submarine. 4 messengers are passed under the hull, 2 forward and 2 aft. Each pair of messengers must be precisely 10 meters, center to center. With the 4 messengers buoyed off, the lift ships are positioned so that each messenger is aligned with a gantry. The ships are each positioned in a 4-point moor. The bow anchors form 2 legs of the moor, and mooring wires off the stern form the other 2 legs. Adjustable pontoons space the ships at the distance previously determined by the planners. A series of spring and breast lines are passed, locking the ships in a nest. This completes the mooring. To avoid confusion with other rigging, the mooring wires will not be shown for the remainder of the sequence. Using a single lift ship and a single stern gantry for illustration, we will show a common method whereby the lift ship can rig itself without assistance from another craft. A 1-inch wire is led over the stern roller and shackled to the inboard leg of the messenger. The buoy is cast off. Another 1-inch wire is led over the gantry roller and shackled to the outboard leg of the messenger. That buoy is cast off. The original messenger is hauled in, drawing the 1-inch wire under the submarine. This wire now becomes the messenger for the lifting wire. The lifting wire is brought out on deck and doubled up. The bight is positioned just forward of the gantry. The messenger is bent to the bight of the lifting wire. The lift wire is hauled outboard over the stern rollers under the submarine and back up the other side. Let's pause a moment and take a look at the purchase arrangement on the end of the gantry. There is a fixed block, an integral part of the gantry structure, a traveling block, and a roller shackle, which is an integral part of the traveling block. The bight of the lifting wire is hauled up until it is even with or slightly above the roller shackle. The roller shackle is opened and the bight laid on the sheave. The gantry purchase is paid out until the roller shackle is 3 feet above the submarine's highest hull projection. Now we'll pause to look at the deck tackle. The lifting force on the wire is exerted through heavy-duty tackle rigged along most of the lift ship's deck. There's a fixed block forward, which is an integral part of the deck structure, and a traveling block aft. The bitter ends of the lift wire are led around the top and bottom grooves of the traveling block's thimble. 2 boulevant clamps are set on each wire. Now let's look at both gantries, fully rigged and ready for the lift. Each ship controls its share of the lift by means of 4 winches. The 2 forward winches haul in on the deck tackle, exerting a pull over the stern rollers of 150 tons each. The after winches exert a pull of 150 tons each over the gantries. All slack is taken out of the lifting wires, and each pair of winches is mechanically engaged to work in unison during the lifting operation. This ensures that the lifting force is distributed equally between the lifting wires. When both ships are fully rigged, their bows are ballasted down. This improves stability during the lift. If this were not done, the bows would rise too far during the lift, and a great deal of stability would be lost. When all rigging and ballasting is completed, the lift begins. An equal strain is taken on all deck tackle and gantry tackle, and the submarine is raised. Precise control of the lifting operation must be exercised to ensure that the submarine's trim and transverse stability is maintained. When the submarine has broken the surface, the entire nest is moved to a suitable grounding point. When using the belly lift method, the ships are moored on either side of the submarine and spaced by spud pontoons a distance equal to the submarine's beam. The strain of the lift is borne by lifting bits mounted in pairs along each side of the lift ship. These bits are commonly called pinpoints. Lifting wires are rigged in matched pairs. The first wire is led by messenger from the outboard pinpoints of one ship under the submarine and stopped off to the matching inboard pinpoints of the second ship. A belaying stopper, an integral part of the lift ship's deck edge, temporarily holds the wire. Meanwhile, the mate to this wire is passed from the second ship and is stopped off at the matching inboard pinpoints of the first ship. In similar manner, all lifting wires are passed. As low tide approaches, the lift ships are ballasted down. The belaying stoppers are released, and all slack is taken out of the wires. The belaying stoppers are again set. At low tide, the wires are pinned down. In pinning down, the wire is led in a figure 8 around the set of pinpoints and secured in a clamp. Like the belaying stoppers, these clamps are an integral part of the lift ship's deck structure. The belaying stoppers are released. When the lift begins, the full strain of the lift will be carried by the pinpoints. The lift ships are now pinned down and fully ballasted. Any rise in tide or change in ballast will lift the ships as well as the submarine. As the tide floods, the submarine is raised the distance of the tide range, plus approximately 16 inches, contributed by the simultaneous deballasting of the lift ships. The nest can now be moved to shallower water, regrounded, and the process repeated. Ever since the Navy launched its first submarine at the turn of the century, accidental sinking has been an ever-present threat, regardless of how new the ship is or how experienced her crew. In recent years, some of our largest, most modern submarines have been claimed by the sea. In spite of the fact that recent losses were in deep water, the great majority of sinkings occur near our coasts, well within the limits of the continental shelf. In fact, 2/3 of all American submarine losses, other than combat losses, occurred in depths less than 300 feet, placing the submarine well within reach of present-day diving technology. The results of past operations often provide the foundation for new hull designs, such as the ATS, and past operations also provide the best guidelines for today's new generation of officers and men, any of whom may be called upon at a moment's notice to plan and to execute a submarine salvage operation.